What if a single human lifetime could carry us farther than Mars, farther than Pluto, perhaps even toward another star? Tonight, on Sleepy Space, we'll gently explore how far humans could actually travel through space before one life comes to an end, from today's rockets to the strange doorway of relativity. Before we begin, tell us where on Earth you're listening from. If a human being left Earth tonight, not as a symbol, not as a myth, not as a glowing figure in a science fiction painting, but as a living body sealed inside a real spacecraft, breathing recycled air, carrying a finite heart, finite bones, finite years, and every quiet weakness that belongs to biology, the first question would not be how brave they are, or how beautiful the stars look through the window, but how far a single human lifetime can truly stretch when it is placed beside the speed of light. On Earth, a lifetime feels vast because we live inside it slowly. 80 years can hold childhood, language, love, grief, work, seasons, the fading of faces, the building and breaking of homes, and the long, soft accumulation of memory. Yet the universe does not measure distance by the emotional weight of our years. It measures distance through motion, geometry, energy, and time. And the most honest ruler we possess is light itself, moving through vacuum at about 186,000 miles per second, or roughly 300,000 kilometers per second, fast enough to cross the distance from New York to Los Angeles in a tiny fraction of a blink, fast enough to circle Earth several times in 1 second, and still, in the deeper architecture of space, slow enough to need more than 4 years to reach the nearest neighboring star system. That is the first quiet shock hidden inside the question. Even light, the universal speed limit for information and ordinary causality as modern physics understands it, does not make the cosmos feel small. It only gives us a way to understand how enormous it really is. The moon, the farthest world humans have ever walked upon, is only about 1.3 light seconds away, meaning that moonlight reaches us after a delay shorter than a calm breath. And the Apollo astronauts, traveling in machines of astonishing precision but modest cosmic speed, crossed that gulf in a few days. The sun is about 8 light minutes away, so every sunset is already old when it touches your eyes, a golden message sent from the recent past. Mars can be several light minutes away when near, and more than 20 light minutes away when far, which means a future astronaut on the red planet will never have a real-time conversation with Earth, only a delayed exchange of voices drifting across orbital silence. Jupiter is tens of light minutes away, Saturn more than an hour at many points in its orbit. And by the time we speak of the outer solar system, we are no longer simply measuring distance. We are measuring isolation. But even all of this remains local. It is still the neighborhood of the sun, the warm gravitational province in which Earth was born. And it is easy to mistake that neighborhood for the beginning of interstellar space until one remembers Proxima Centauri, the nearest known star to the Sun, sitting about 4.25 light-years away, Not light minutes, not light hours, but light years. A distance so large that the fastest message nature allows would still take more than 4 years to arrive. And any spacecraft moving far below light speed would need far longer than a human life unless its velocity entered an entirely different class from anything humans have ever ridden. To understand why this matters, we have to separate 3 ideas that ordinary language blends together: distance traveled, destination reached, and survival sustained. A machine can travel far if it is patient, cold, and mostly indifferent to time. The Voyager spacecraft, launched in 1977, have become humanity's most poetic pieces of drifting engineering, carrying instruments, memories, and silence beyond the planets. Yet, even after nearly half a century, they have only reached a distance measured on the scale of light hours, not light years. A human being is different. A human traveler must carry a livable pressure, breathable air, drinkable water, food, waste recycling, thermal control, radiation protection, medical support, psychological stability, and some substitute for the planetary conditions that shaped every cell in the body. In that sense, asking how far humans can travel in one lifetime is not the same as asking how fast a probe can coast after launch. It is asking how far we can carry a small, fragile version of Earth into an environment that does not naturally provide Earth-like mercy. Historically, this realization came in layers. Newton gave humanity the language of gravity and motion, showing that planets and falling apples obeyed the same mathematical order, and this turned the heavens from a divine ceiling into a calculable system. Kepler's ellipses made planetary paths precise. Tsiolkovsky, Obert, Goddard, and later the engineers of the space age translated the dream of leaving Earth into rocketry, where every increase in velocity must be paid for with propellant, mass ratios, exhaust speeds, and unforgiving arithmetic. Einstein then deepened the stage itself, showing that space and time are not fixed backgrounds, but a unified fabric in which motion changes the measurement of duration and distance. These ideas do not make interstellar travel impossible, but they remove the comforting simplicity from it. A spacecraft is not a boat crossing an ocean, because an ocean provides buoyancy and a shore, while space provides almost nothing except vacuum, radiation, gravity wells, and the severe honesty of inertia. If you want to move faster, you must give the spacecraft kinetic energy. In the ordinary approximation, that energy rises with the square of velocity, so 10 times the speed demands about 100 times the kinetic energy for the same mass, before even counting the fuel needed to produce that motion. When speeds become a significant fraction of light speed, relativity makes the energy demand steeper still, not because nature is being cruel, but because mass energy and space-time are bound by deeper rules than human impatience. This is why 1% of light speed, which sounds small beside the full speed of light, is already an almost fantastical velocity for a crude vehicle. About 1,860 miles per second, or 3,000 kilometers per second. At that speed, a ship would cross 1 light year in 100 years. So Proxima Centauri would still take more than 4 centuries, far beyond a single ordinary lifetime. At 10% of light speed, Proxima enters the outer edge of human-scale possibility. roughly 42 or 43 years of cruise time in a simple, idealized calculation, not including acceleration, deceleration, system failures, course corrections, shielding losses, or the long human cost of spending most of adulthood inside a moving habitat. At half the speed of light, nearby stars begin to feel reachable within years or decades. But the energy, shielding, and braking requirements become so extreme that the ship is no longer merely a vehicle. It becomes a civilization-scale object, a concentrated decision made by an entire technological species. And yet, the universe has one more strange layer, one that makes the question almost dreamlike without making it magical. According to special relativity, time passes differently for travelers moving very fast relative to Earth. At ordinary spacecraft speeds, the difference is tiny, but near the speed of light, a traveler's clock can tick noticeably slower than clocks left behind. This means that one lifetime is not a perfectly simple phrase. One lifetime, according to whom? The people waiting on Earth, aging under the same blue sky? Or the traveler on the ship, aging according to the proper time carried along their path through space-time? In principle, a sufficiently fast ship could allow a traveler to experience a shorter journey than Earth observers measure, because time dilation and length contraction reshape the journey from the traveler's frame of reference. But this is not a shortcut around physics. It does not permit faster-than-light travel, and it does not return the traveler to the same historical moment they left. It simply means that the cost of distance may be paid partly in separation from Earth's future, so that a traveler who crosses great distances might arrive with decades in their body while centuries have passed at home. That thought is scientifically serious and emotionally enormous. It means the limit of travel is not only mechanical, but human in the deepest sense. A journey to the stars would stretch identity, memory, and belonging as much as it stretches engineering. For Chapter 1, then, the most truthful answer is also the most humbling. Measured against light, a human lifetime is long enough to transform a planet-bound species into a spacefaring one, long enough to reach the Moon, perhaps Mars, perhaps deeper stations in the solar system, but not long enough for ordinary technology to make the stars feel near. To reach another star within one life, humans would need velocities not merely faster than today's spacecraft, but orders of magnitude beyond them, along with protection from radiation, artificial or partial gravity, closed ecological systems, autonomous repair, advanced propulsion, and the ability to slow down after arriving. The great mistake would be to say the universe forbids us. The greater mistake would be to say it will be easy. The truth rests quietly between those extremes. Physics leaves a narrow, difficult door open, while biology and engineering remind us that walking through it may require a version of civilization more patient, more powerful, and more unified than anything we have yet become. So when we ask how far one person can travel in space before their lifetime closes, we are really asking how far Earth itself can be miniaturized, protected, accelerated, and carried into the dark. We are asking how much of home must fit inside a vessel before the human body can survive the absence of home. And as the stars continue to burn in their ancient distances, the answer waits not as a single number, but as a layered horizon. With today's machines, the solar system. With revolutionary propulsion, the nearest stars. With relativistic flight, perhaps far beyond the intuition of ordinary time, though never without cost. A lifetime seen from Earth is a candle. Light is a storm. The galaxy is an ocean so wide that even light crosses it like a patient tide. And somewhere between the candle and the ocean stands the human traveler, small, awake, breathing softly inside a machine, learning that the first step toward the stars is not speed, but understanding the true scale of the night. If we stay with present-day technology, not the glowing technology of distant centuries, not engines that exist only as equations on a whiteboard, but the rockets, capsules, life support systems, orbital mechanics, materials, radiation models, mission architectures, and human medical data that actually belong to our era, then the answer becomes both humbling and strangely beautiful. Humans can travel farther than any creature on Earth was ever meant to travel, yet still remain almost entirely inside the sun's small island of influence. The real frontier of current human spaceflight is not the nearest star, or even the outer planets, but a layered region beginning in low Earth orbit, extending outward to the Moon, then cautiously toward Mars, and only in more ambitious, less proven forms toward near-Earth asteroids or deeper stations in the inner solar system. Low Earth orbit, where humans have lived continuously aboard space stations, is only a few hundred miles above the surface, so close in cosmic terms that if Earth were reduced to the size of a classroom globe, the orbiting station would skim just above the paint. Yet, reaching that narrow shell requires a spacecraft to move sideways at roughly 17,500 miles per hour, fast enough to keep falling around Earth without striking it, which is why orbit is not simply up, but a precise state of perpetual falling governed by Newton's mechanics and refined through centuries of celestial mathematics. From the ground, launch looks like brute force, fire lifting metal into the sky, but beneath the flame is geometry. The rocket must climb out of the thickest atmosphere, turn sideways in a gravity turn, shed stages or mass, and insert itself into a path where gravity becomes not an enemy, but the curve that holds the vehicle in motion. This is the first real human range in space, and it has taught us almost everything we know directly about living away from Earth. How bones lose density in microgravity, how muscles weaken without load, how fluids shift toward the head, how carbon dioxide pockets can form in still air, how water can be recycled, how isolation changes the mind, and how a spacecraft is less like an airplane and more like a small artificial ecosystem that must keep its passengers alive every second. But low Earth orbit is not far. It is the harbor. The Moon is the first true crossing. At roughly 238,900 miles away on average, the Moon sits about 1.3 light seconds from Earth, which makes it unimaginably distant by ancient human standards and almost touchingly close by astronomical standards. The Apollo missions proved that humans can cross that distance, land, walk, work, collect samples, and return. But they also revealed how narrow the margin was. Small crews, short stays, limited supplies, no real long-term shelter, and no ability to live off the lunar environment. With current and near-current technology, returning humans to the moon is far more realistic than sending them anywhere else beyond Earth. Because the moon is close enough for communications delay to be small, close enough for emergency planning to remain meaningful, and close enough that mission durations can be measured in days or weeks rather than many months. Yet even this nearby gray world is not friendly. It has no breathable air, no ocean, no weather, no global magnetic shield like Earth's, no thick atmosphere to soften radiation or burn up micrometeoroids, and only 1/6 of Earth's gravity, a level whose long-term effects on human physiology remain uncertain. A sustained lunar presence would require pressurized habitats, radiation shielding, perhaps made partly from buried regolith, reliable power through the long lunar night, or at polar sites with favorable illumination, water extraction if polar ice can be accessed safely and economically, and systems for maintenance that do not depend on constant rescue from Earth. The moon, then, is not merely a destination. It is the first test of whether humans can stop visiting space and begin residing there. Mars is the next great answer, and it is where current technology starts to become stretched almost to its philosophical limit. Mars is not a few days away. It is a moving planet on its own orbit, sometimes tens of millions of miles distant, sometimes far more. And any efficient journey must respect the choreography of 2 planets circling the Sun. Mission planners often speak in terms of launch windows, roughly every 26 months, transfer times of many months, and surface stays that may be short and difficult, or long enough to wait for the planets to align again. A simple, popular phrase like "going to Mars" hides a full celestial mechanism: Hohmann-like transfers, departure energy, arrival capture, entry through a thin but dangerous atmosphere, supersonic descent, landing heavy payloads, surface radiation, dust, power supply, ascent from Mars, and return trajectory. Mars has a day length similar to Earth's: ancient river valleys, polar ice, volcanoes, canyons, and a sky that can glow butterscotch through dust, which makes it emotionally easier to imagine as a human world. Yet that familiarity is deceptive. Its atmosphere is mostly carbon dioxide and less than 1% of Earth's sea level pressure. Its average temperatures are brutally cold. Its global magnetic field is gone, and radiation exposure during the trip and on the surface remains one of the central biomedical concerns. If humans travel to Mars using present chemical propulsion and realistic mission designs, the journey is possible in principle, but not yet demonstrated. The technology pieces exist in partial form, but integrating them into a safe round-trip human mission is a much larger achievement than sending rovers, because a rover can fail silently, while a crew cannot. Beyond Mars, the map becomes more speculative for human travelers, even if robotic spacecraft have already shown us the way. Near-Earth asteroids may in some cases be energetically accessible, because orbital energy does not always correspond to visual distance. and a small asteroid with a favorable path can be easier to reach than a planet's deep gravity well. But living near or on an asteroid would be deeply strange. Almost no gravity, no atmosphere, no shielding, irregular terrain, uncertain resources, and constant dependence on anchoring, propulsion, and habitat integrity. The asteroid belt between Mars and Jupiter is farther still, and although it offers scientific and resource interest, it is not a natural stepping stone for ordinary crews with current systems. Jupiter's realm is magnificent but severe. Its moons, especially Europa, Ganymede, and Callisto, are scientifically irresistible because of ice, possible subsurface oceans, and complex histories. But the Jovian radiation environment, especially near Europa, is dangerous. The travel time is long, solar power is weaker, and communication delays become long enough that crews must be far more autonomous. Saturn, with Titan and Enceladus, invites even deeper wonder. Titan has a thick, nitrogen-rich atmosphere and methane lakes beneath an orange haze, while Enceladus throws plumes from a hidden ocean into space. But for humans, these worlds are so distant that a mission would last years to decades unless propulsion improves dramatically. By the time we speak of Uranus, Neptune, Pluto, or the Kuiper Belt, present human technology no longer describes a mission in the familiar sense. It describes a lifetime sealed inside machinery, with no quick rescue, little sunlight, enormous communication delay, and a requirement for closed-loop life support far beyond what we have proven. This is where the difference between robotic reach and human reach becomes decisive. Robots have crossed the solar system because they can be small, patient, cold, and expendable. Humans require volume, shielding, food, water, medicine, maintenance, and psychological continuity. Voyager can coast through darkness for decades with fading power and no fear. A crew cannot. New Horizons could flash past Pluto after a long cruise and return data. A human mission would need to arrive alive, slow down, or survive a flyby, function, communicate, and continue supporting bodies that age, heal, worry, and sleep. So if we answer with strict honesty, current technology places the practical human frontier at the Moon, the aspirational frontier at Mars, and the conceptual edge somewhere among near-Earth asteroids or early deep space habitats, while the outer solar system remains a realm for robots until propulsion, radiation protection, artificial gravity or countermeasures, autonomous medicine, and closed ecological systems advance far beyond today's demonstrated level. This does not make the age small. It makes it early. The first ocean voyagers did not cross every sea at once. They learned winds, hulls, stars, currents, disease, food storage, and navigation, one terror at a time. Space is harsher than any ocean because it provides no air, no buoyancy, no edible wilderness, no natural shelter, and no forgiving shore. But the same pattern of expansion may hold. First, the harbor of orbit, then the nearby island of the Moon, then the red desert of Mars, then the scattered rocks and icy moons farther out. In one human lifetime, using what we can seriously build from today's technological foundation, we do not reach another star. and we likely do not make the outer planets ordinary human destinations. We become, at best, a species learning to live in the inner solar system. And yet, that is not a failure. To stand on Mars and see Earth as a bright evening star would already mean that life has crossed a boundary 4 billion years in the making. To sleep beneath lunar regolith while Earth hangs blue and silent overhead would already mean that a creature born from oceans has learned to carry its ocean within a machine. The honest distance of current human travel is therefore not measured only in miles, but in how far we can extend the conditions of home without breaking them. For now, the stars remain beyond a single human lifetime by any technology we have actually proven. The moon waits close. Mars waits hard. The asteroids wait quietly, and the outer planets wait like cathedral bells in the dark. Current technology does not give us the galaxy. It gives us the first rooms beyond Earth, and perhaps that is exactly where a young spacefaring species must begin. The strange thing about speed in space is that it can look almost godlike from the ground and still be painfully slow beside the stars. Because a rocket leaving Earth does not merely rise like a flame escaping gravity. It enters a mathematical landscape where every mile per second has been purchased with fuel, mass, heat, staging, guidance, and the hard patience of orbital mechanics. When a launch vehicle climbs through the atmosphere, its motion appears violent and absolute. But after the first few minutes, the drama becomes quieter and more precise. The rocket must turn sideways, build horizontal velocity, and fall around Earth fast enough to miss the ground again and again, which means even the act of reaching orbit is less like climbing a tower and more like joining a curved path written by Newton's laws. Low Earth orbit requires a speed of roughly 17,500 miles per hour, a number that feels enormous to any human imagination shaped by highways and airplanes. Yet that velocity is only about 0.0026% of the speed of light. The comparison is almost unfair, but it is necessary because the stars do not respond to human feelings of speed. They respond only to distance divided by velocity, and in that arithmetic, even our fastest crewed spacecraft belong to the first whispers of motion. The Apollo missions reached the moon in a few days, not because their spacecraft were fast in an interstellar sense, but because the moon is close in the language of light, only about 1.3 light seconds away. A journey that changed human history took place inside a bubble of space so small that light crosses it in the time it takes to breathe. Mars already stretches the same technology into a harsher scale, where months of transfer replace days. Launch windows depend on planetary alignment, and the difference between a close opposition and a far configuration can reshape mission planning. But even Mars, for all its red distance and mythic weight, is still a neighbor inside the Sun's household. The nearest star, Proxima Centauri, is about 4.25 light-years away, and that single fact quietly destroys the illusion that faster rockets alone will solve the problem. A spacecraft moving at 25,000 miles per hour, a speed that sounds almost unreal on Earth, would need tens of thousands of years to cross that gulf if it were pointed correctly and kept moving without meaningful slowdown. Even Voyager 1, one of the fastest and farthest emissaries humanity has ever sent outward, is not on a practical, crude route to another star, and would still require a timescale far beyond civilization as we ordinarily remember it to reach stellar distances. The reason is not a lack of courage, nor merely a lack of better engines. It is that current spacecraft speeds are built for the solar system, and the solar system is tiny compared with the spaces between suns. To see the structure of the problem, imagine velocity as a ladder. The first rung is orbital speed, enough to circle Earth. The next rungs are escape trajectories, lunar transfers, interplanetary cruise speeds, gravity assists, and deep space flybys. These rungs are difficult, beautiful, and historically monumental, but the rung required for interstellar travel in one lifetime is not just a little higher, it is on another wall. 1% of light speed is about 1,860 miles per second, or 3,000 kilometers per second, and even that would take roughly 425 years to reach Proxima Centauri in a simple straight-line estimate. 10% of light speed would bring the crossing down to about 42 or 43 years, finally entering the outer boundary of a human lifetime. But 10% of light speed is so far beyond crude spacecraft today that it should be treated not as an engineering upgrade, but as a civilization-scale transformation. The heart of this transformation is energy. In classical mechanics, kinetic energy is 1/2 times mass times velocity squared, which means speed becomes expensive very quickly. Doubling velocity does not merely double the energy, it quadruples it. Increasing velocity by a factor of 100 increases kinetic energy by a factor of 10,000 for the same mass. Before considering the additional propellant and machinery required to reach that speed, and as velocity becomes a significant fraction of light speed, special relativity enters the calculation, making the energy demand rise even more severely as the spacecraft approaches the cosmic speed limit. This is why the phrase, "just go faster," is one of the most innocent misunderstandings in spaceflight. A spacecraft is not a car with a larger engine. It is a system that must carry, expel, or receive momentum, and every method has a cost. Chemical rockets, the magnificent engines that opened the space age, work by throwing exhaust backward at high speed, but their exhaust velocity is limited by the energy of chemical bonds. They are superb for leaving Earth, entering orbit, and sending payloads across the solar system with clever trajectories. Yet they cannot push a large, crude habitat anywhere near a meaningful fraction of light speed without collapsing under the tyranny of the rocket equation. That equation, first understood in its modern form through the work of Konstantin Tsiolkovsky, tells us that the velocity change a rocket can achieve depends on exhaust velocity and the logarithm of the ratio between its initial and final mass. The logarithm is the quiet trap. Add more propellant and the rocket gets heavier. Add more propellant to push that propellant and the mass grows again. Beyond a certain point, brute force becomes self-defeating. This is why staging was necessary to reach orbit, why mission planners use gravity assists, why interplanetary spacecraft often follow elegant arcs instead of direct lines, and why the dream of interstellar flight demands propulsion that is not merely bigger, but fundamentally different. Ion engines and electric propulsion offer one kind of answer, by using propellant more efficiently, accelerating ions to high exhaust velocities, and producing gentle thrust over long durations. For robotic probes, this is powerful, almost meditative technology. A faint push, sustained over months, can become a large change in velocity. But for a crewed interstellar vessel, the thrust must also support mission timelines compatible with biology, maintenance, and human psychology. A whispering engine may be efficient, but if it takes years just to build up speed and cannot move a massive shielded habitat quickly enough, its elegance remains trapped inside smaller missions. Nuclear thermal propulsion offers another step, using a reactor to heat propellant far beyond ordinary chemical limits, and it may reduce travel times to Mars or improve deep solar system access. Nuclear electric systems could power high-efficiency thrusters for long journeys. Fusion concepts, if ever made practical in compact and reliable form, could move the boundary farther still. Yet even these possibilities do not automatically produce a ship that reaches the nearest star in one lifetime, because interstellar velocity is not a single number. It is a whole chain of requirements: acceleration, cruise, shielding, navigation, deceleration, heat rejection, reliability over decades, and the survival of passengers who cannot be treated like instruments bolted to a frame. The sun itself shows us the scale of the energies involved, burning through nuclear fusion in its core, releasing power far beyond any machine humanity has built, and even then, its light needs years to cross the nearest stellar gap. Another reason current speed is too slow lies in the geometry of space travel. Spacecraft rarely move in straight lines as imagined in children's drawings. They move through gravitational fields, along conic sections and patched trajectories, shaped by the sun's pull and the motion of planets. A gravity assist around Jupiter or another planet can steal a little orbital energy from that planet, reshaping a probe's path and increasing its speed relative to the sun, a technique used brilliantly by robotic missions. But this is not a magic slingshot to the stars. It works within the energy economy of the solar system, and the gains, while extraordinary for exploration, remain tiny compared with the velocities needed to cross light years in decades. Parker's solar probe can reach breathtaking speeds near the sun because it falls deep into the sun's gravitational well. But that speed belongs to a solar orbit and a specialized thermal environment, not to a crude starship coasting safely toward Alpha Centauri. The distinction matters because spaceflight numbers can seduce us when stripped from context. A probe may be fastest near perihelion. A spacecraft may have a high heliocentric speed. A flyby may produce a spectacular relative velocity. Yet, none of these automatically describes a human-capable interstellar cruise. And even if a future machine could accelerate a crewed vessel to 1/10 of light speed, the ship would meet a darker problem. At that speed, dust is no longer dust in the ordinary sense. A tiny grain of interstellar material striking the forward shield would carry enormous kinetic energy. Gas atoms would arrive as a high-speed particle stream. The emptiness between stars is not perfectly empty. It is thin, silent, and dangerous when crossed too quickly. Current spacecraft survive space partly because they move at solar system speeds through environments we can model and shield against within reason. A relativistic or near-relativistic spacecraft would need a forward architecture unlike anything now flown, perhaps layered shields, magnetic deflection, sacrificial material, or active detection systems that turn the ship into something more like a moving fortress than a vessel. Then comes the forgotten half of speed: stopping. A spacecraft that reaches another star at 10% of light speed but cannot slow down would flash through the system in a brief scientific flyby, useful for a probe, almost tragic for humans. To arrive is not merely to pass near a destination. It is to reduce velocity, enter a usable trajectory, survive local hazards, and remain long enough for the journey to have human meaning. Deceleration requires energy or interaction with the destination system, and there is no guarantee of convenient fuel waiting at the far end. Every serious answer to one lifetime interstellar travel must include braking, and braking doubles the depth of the energy problem. This is why present-day speed is too slow in a way that is not psychological but structural. Our rockets were born to escape planets and explore a star system, not to cross the deserts between stars within a human life. The distances are light years, while our crude velocities are miles per second. The equations do not mock us. They clarify the path. They tell us that the moon belongs to days, Mars to months, the outer planets to years or decades, and the nearest stars to either thousands of years at current speeds or entirely new propulsion at future speeds. The quiet beauty of this is that it gives humanity a true map, not a fantasy. We are not standing before an impossible wall, but before a scale we have only begun to understand. To travel farther, we must learn not only to build faster engines, but to command energy with the patience of physics, to protect living bodies from the violence of velocity, and to remember that between one star and the next, even speed becomes a form of humility. The farther a human being travels from Earth, the more distance stops being only a matter of miles and becomes a slow biological negotiation. Because the body that looks so capable beneath sunlight is, in truth, a carefully balanced, planet-made instrument, tuned by evolution to one atmosphere, one gravity, one magnetic shield, one day-night rhythm, one microbial world, and one blue horizon that has always been nearby. A spacecraft can be engineered from aluminum, composites, ceramics, titanium, carbon fiber, and layers of insulation. And if its electronics are hardened well enough, it may sleep through years of darkness without fear. But a human body cannot be treated as cargo in the same way, because it is warm, wet, electrically alive, chemically restless, and constantly repairing damage faster than most people realize. Every heartbeat assumes pressure. Every bone assumes load. Every cell assumes a radiation environment softened by Earth's atmosphere and magnetosphere. Every sleep cycle assumes a sky that darkens and brightens with the turning of a world. This is why the biological cost of distance is not an afterthought to interplanetary or interstellar travel. It is one of the central equations, even if it is written not only in mathematics, but in blood chemistry, bone density, immune response, stress hormones, circadian timing, and the quiet endurance of the mind. In low Earth orbit, where astronauts have spent months aboard space stations, we have already seen that the body begins adapting almost immediately to weightlessness, and adaptation in space is not always health in the earthly sense. Without the constant downward pull of gravity, muscles no longer work against body weight in the ordinary way, especially the muscles of the legs, back, and posture. So they weaken unless exercise becomes a daily medical requirement rather than a lifestyle choice. Bones, especially weight-bearing bones, lose mineral density because the skeleton is no longer being loaded as it was on Earth, and the body begins to remodel itself for a world where standing is unnecessary. This is not a dramatic instant failure. It is slower and therefore more unsettling. A gradual rewriting of the body's assumptions. Treadmills with harnesses, resistive exercise devices, cycling systems, careful nutrition, vitamin D, and medical monitoring can reduce these losses. But they do not turn microgravity into Earth. A mission to Mars lasting many months each way, followed by time in only about 38% of Earth's gravity, raises a question we have not yet answered with complete confidence. How much gravity does the human body need to remain healthy across years? And is lunar gravity, Martian gravity, or rotating artificial gravity enough to preserve the deep architecture of human physiology? The answer matters because distance increases duration, and duration turns small changes into mission-defining risks. In weightlessness, fluids shift upward toward the head, changing facial appearance, nasal congestion, intracranial pressure, and possibly contributing to vision changes observed in some astronauts, a condition often discussed under spaceflight-associated neuroocular concerns. The heart and blood vessels adapt to an environment where pumping blood upward against gravity is no longer the same task, and when astronauts return to Earth, they can feel dizzy or weak because the cardiovascular system must suddenly remember a planet. The vestibular system, the inner ear machinery that helps the brain understand balance and motion, can become confused when there is no stable down, producing space motion sickness early in flight and requiring the brain to build a new map of orientation. None of this makes spaceflight impossible, but it reminds us that the human body is not a neutral passenger. It is an active participant being reshaped by the journey. Radiation is even less forgiving because, beyond Earth's protective magnetic field, the traveler enters a particle environment that no human species evolved to inhabit. There are solar particle events, sudden storms from the sun that can release intense streams of energetic particles, and there are galactic cosmic rays, high-energy particles arriving from outside the solar system, often moving so fast and striking so deeply that simple shielding becomes complicated. A solar storm can be handled in part by a storm shelter inside the spacecraft, a protected region surrounded by water, food supplies, equipment, or hydrogen-rich materials that reduce exposure. But galactic cosmic rays are more persistent and harder to block, because when very energetic particles hit shielding, they can create secondary radiation that also matters biologically. Distance from Earth means longer exposure, and longer exposure means increased concern for cancer risk, central nervous system effects, cardiovascular impacts, degenerative tissue changes, and possible effects on cognition, though the details depend on dose rate, particle type, shielding, mission duration, and individual biology. For a short lunar mission, radiation is a managed hazard. For a Mars mission, it becomes a major design driver. For a multi-decade interstellar voyage, it becomes part of the fundamental architecture of the ship. A true deep space habitat may need to place crew quarters behind water walls, fuel tanks, polyethylene-like materials, regolith in surface bases, or perhaps one day, active magnetic or electrostatic shielding, though active shielding remains technically difficult because generating a protective field strong and reliable enough without introducing new hazards is not a solved engineering reality. The body also depends on an immune system that is shaped by Earth's microbial and gravitational environment, and spaceflight appears to alter immune regulation, inflammation, latent virus behavior, wound healing, and microbial communities in ways still being investigated. A closed spacecraft is not sterile. It is an ecology. Human skin, breath, gut bacteria, food systems, water loops, filters, surfaces, and hidden moisture all create a small living world. And over time, microorganisms can form biofilms, adapt to niches, affect equipment, or shift in balance. On Earth, vast ecosystems dilute and buffer microbial life. But inside a spacecraft, every organism is a resident of the same sealed village. This means life support cannot be only mechanical. It must be ecological, medical, and continuously watched. Water recycling, carbon dioxide removal, oxygen generation, humidity control, trace contaminant monitoring, and waste processing must function, not as conveniences, but as organs of the spacecraft. And the farther the crew travels, the less acceptable it becomes to rely on resupply. The spacecraft becomes a lung, kidney, stomach, skin, and shelter, built in metal and software. If one system falters near Earth, help may be possible. If it falters on the way to Mars, the crew must diagnose and repair it. If it falters between stars, the distinction between engineering and survival disappears entirely. Then there is the mind, which may be the most delicate long-duration instrument of all. Humans can endure hardship with extraordinary resilience when meaning is clear, social bonds are healthy, and environments provide rhythm, privacy, beauty, and agency. But deep space removes many ancient stabilizers at once. There is no weather, no open landscape, no natural soundscape, no spontaneous community outside the crew, no quick return, and eventually, no real-time conversation with Earth. A Mars crew will already experience communication delays of several to more than 20 minutes one way, depending on planetary positions, turning every conversation with home into a correspondence rather than a call. Beyond Mars, delay becomes longer still, and in interstellar space, Earth becomes not a control room, but a memory, transmitting slowly across years. Isolation and confinement are therefore not soft problems. They are mission systems. Crew selection, interpersonal dynamics, cultural compatibility, conflict resolution, sleep hygiene, workload design, lighting cycles, private space, shared rituals, exercise, entertainment, autonomy, and the psychological presence of Earth through messages and archives all become part of the biological cost of distance. A ship traveling for decades would need more than discipline. It would need a livable culture. It would need ways for grief, boredom, wonder, fear, and purpose to move through the crew without poisoning the closed emotional atmosphere. Medicine grows more difficult as distance grows, because Earth medicine depends on abundance, specialists, laboratories, imaging machines, pharmacies, blood banks, sterile operating rooms, replacement parts, and the ability to move a patient to a higher level of care. A deep space crew cannot carry every hospital, yet it must be prepared for injury, infection, dental emergencies, kidney stones, allergic reactions, psychological crises, equipment-related accidents, pregnancy questions if missions become generational, and ordinary aging if travel lasts decades. Artificial intelligence may help with diagnosis. Robotic systems may assist procedures. Compact labs may analyze blood and microbes. 3D printers may produce tools, and synthetic biology may one day manufacture medications on demand. But each possibility adds complexity, mass, power demands, and new failure modes. Even sleep becomes a technical subject because circadian rhythm relies on light timing, activity, temperature, social cues, and hormonal cycles. On a spacecraft, lighting may have to imitate sunrise and sunset with deliberate precision, not for romance, but for endocrine stability and cognitive performance. Nutrition is equally layered. Calories are simple compared with the long-term challenge of preserving vitamins, maintaining gut health, preventing muscle and bone loss, supporting immunity, and keeping food psychologically acceptable after months or years of repetition. If plants are grown on board, they become food, atmosphere processors, humidity regulators, microbial habitats, and emotional companions. Their green leaves offering a reminder that life can still unfold slowly under artificial suns. The deeper lesson is that distance multiplies every biological requirement by time. A 3-day lunar transit can tolerate limits that a 6-month Mars cruise cannot. A 3-year mission demands redundancy that a 3-week mission does not. A 40-year journey to a nearby star, even at extraordinary speed, would demand not just a spacecraft, but a stable human environment capable of preserving bodies and minds across a major fraction of life. Artificial gravity by rotation may become essential for such durations, but rotating habitats introduce engineering trade-offs: radius, spin rate, structural stress, docking mechanics, motion sickness, and mass. Hibernation, or metabolic suppression, is sometimes imagined as a way to reduce life support demands. And while medical research into torpor-like states is scientifically interesting, long-term human suspended animation remains speculative and should be treated as a possibility under investigation rather than a solved answer. Genetic adaptation, biomedical enhancement, or engineered radiation resistance appear in future-oriented discussions, but they carry scientific uncertainty and ethical weight, especially when the traveler is no longer merely using a machine, but changing the definition of the spacefaring human. So the biological price of distance is finally this: the farther we go, the more completely we must replace Earth without pretending we have escaped our dependence on it. We must bring gravity, or imitate it, bring air and renew it, bring water and purify it, bring microbes and manage them, bring medicine and miniaturize it, bring society and keep it gentle enough to survive confinement, bring shielding against particles older than the solar system, and bring enough meaning that the human mind does not become the weakest seal in the vessel. Present technology can keep people alive in orbit and perhaps, with great care, carry them to Mars. But the biological demands of deeper travel rise until the spacecraft must become a small, deliberate biosphere. In the silence beyond Earth, the human body is not a flaw in the mission. It is the reason for the mission, the fragile flame being protected. And as that flame moves farther from the planet that made it, every mile asks the same quiet question. Can a creature built by oceans, forests, weather, sunlight, bacteria, gravity, and touch remain fully human when all of those things must be recreated inside a machine crossing the dark? Energy is the quiet wall at the edge of every dream of the stars, not because the universe lacks romance, and not because human imagination is too small, but because motion itself must be paid for, and the price rises with a severity that no beautiful spacecraft silhouette can soften. A person looking up at the night sky may see stars as points of invitation, scattered calmly across the dark. But a physicist sees another layer beneath that beauty: mass, velocity, momentum, kinetic energy, exhaust speed, thermal waste, structural stress, and the deep accounting of nature that says nothing moves for free. On Earth, we are used to motion being assisted by the world around us. A car pushes against a road. A ship pushes against water. An airplane pushes against air and borrows oxygen from the atmosphere to burn fuel. A rocket is lonelier. It must carry its reaction mass with it, or else find some external way to exchange momentum, because in the vacuum between worlds, there is no road, no river, no wind, no hidden hand to push against. This is why the earliest mathematical dreamers of spaceflight, especially Konstantin Tsiolkovsky, revealed something both empowering and merciless. A rocket can reach space by throwing mass backward, but the velocity it gains depends on the speed of that exhaust and on the logarithm of the mass ratio, the ratio between the fully fueled vehicle and the empty vehicle after propellant is spent. The logarithm is gentle at first and cruel later. Add fuel, and the rocket can go faster. Add too much fuel, and now you need fuel to push the fuel. Add even more, and the vehicle becomes a tower of stored departure. Most of its body sacrificed simply to make a smaller body continue onward. This is not failure. It is the reason staging works, the reason launch vehicles discard empty tanks and engines as they climb, the reason chemical rockets opened the space age, and also the reason chemical rockets cannot simply be enlarged until they become starships. The energy in chemical bonds is magnificent by human standards and modest by interstellar standards. It can lift capsules into orbit, send astronauts toward the moon, launch robotic spacecraft toward Mars, Jupiter, Saturn, Pluto, and beyond. But it does not naturally offer the enormous delta V needed to push a massive crude habitat to a meaningful fraction of the speed of light. The phrase delta V, change in velocity, sounds technical and dry, yet it is one of the most poetic measures in astronautics, because it describes how much freedom a spacecraft has to change its fate. Every burn spends some of that freedom. Leaving Earth spends it. Escaping the sun spends more. Matching speed with a destination spends it again. And interstellar flight does not merely ask for a little more delta V than Mars. It asks for a change in kind. To see the scale, consider the old classical equation for kinetic energy: 1/2 times mass times velocity squared. If the same spacecraft goes twice as fast, it needs 4 times the kinetic energy. If it goes 10 times as fast, it needs 100 times the kinetic energy. If it goes 1,000 times as fast, the number becomes 1,000,000 times larger before relativity even begins to sharpen the curve. And if the ship is not a tiny probe, but a crude vessel carrying shielding, water, food systems, air recycling, radiation shelters, medical equipment, spare parts, computers, engines, propellant, and human living space, then mass quietly becomes the great multiplier of every dream. A gram can be accelerated by ideas that cannot move a city. A wafer-sized probe might someday be pushed by laser light toward another star. But a human starship is not a wafer. It is a protected biosphere with engines. It is a small Earth asking to be thrown into the night. Nuclear energy appears because chemical energy is not enough. Nuclear thermal propulsion, in principle, can heat propellant with a reactor instead of chemical combustion, allowing higher exhaust velocity and therefore better performance for missions across the solar system. Such engines could make Mars easier, shorten certain transfers, and increase payload flexibility. Yet, they still remain far from the velocities that would make another star feel near within a lifetime. Nuclear electric propulsion changes the shape of the problem by using a reactor to generate electricity, then using that electricity to accelerate ions or plasma with great efficiency. Its thrust can be low, almost like a continuous whisper, but over long months, it can reshape a trajectory beautifully, which makes it attractive for cargo, robotic missions, and perhaps deep solar system transport. But whispering thrust has trouble with human impatience and human biology. A crude interstellar vessel must not only be efficient, it must accelerate enough mass fast enough to keep the mission inside lives, not dynasties. Fusion, the process that powers the stars themselves, shines in the imagination because it offers far greater energy per unit mass than chemistry, and might, if controlled in a compact, reliable, high-power system, permit spacecraft that are not merely improved rockets, but new kinds of moving worlds. Concepts involving deuterium, helium-3, pulsed fusion, magnetic confinement, inertial fusion, and fusion-driven plasma exhaust have appeared in serious studies and speculative engineering for decades. But no one should confuse a compelling architecture with a proven vehicle. A fusion starship would need not only sustained reactions, but efficient conversion of fusion energy into directed thrust, protection from neutrons and radiation, thermal management, fuel storage, engine durability, and a mass budget that does not collapse under its own shielding. Antimatter sits even higher on the ladder of energy density, almost frighteningly elegant in theory. Because when matter and antimatter meet, mass can be converted into energy with extraordinary completeness compared with chemical or even nuclear processes. But antimatter is not a fuel humanity can presently manufacture, store, or handle at starship scale. It is produced in tiny quantities at enormous energy cost and must be confined so it never touches ordinary matter until intended. In discussion, it belongs to the outer edge of plausible physics and the far edge of practical engineering, an example of how nature permits immense energy release without promising that civilization can safely bottle it. Then there is the dream of not carrying the main energy source at all. A sail pushed by sunlight is gentle and slow near Earth, but a sail pushed by an immense laser array could, in principle, accelerate a very small spacecraft to a significant fraction of light speed. This is why beamed energy concepts are so fascinating. They loosen the tyranny of carrying propellant by leaving the power plant at home. But here the scale divides like a quiet canyon. A gram-scale probe can be imagined as a thin sail, a chip, a camera, a brief messenger crossing interstellar distance. A human vessel would need mass thousands, millions, perhaps billions of times greater, depending on its design, and the laser system required to push it would become an infrastructure project on the scale of a planetary civilization. The sail must survive heating, remain aligned, avoid tearing, and somehow the ship must still slow down at the destination, unless the mission is only a flyby. Deceleration is the forgotten twin of acceleration, the shadow that waits at the end of every fast journey. To reach Proxima Centauri at 10% light speed and merely flash through the system would be scientifically interesting for a robotic probe and almost useless for a crew hoping to arrive. Arrival means reducing speed, entering a controlled trajectory, surviving local conditions, and having time to observe or live. Braking may require onboard propellant, magnetic sails interacting with stellar winds or interstellar plasma, laser systems at the destination, or other mechanisms still uncertain in engineering detail. Every braking strategy brings mass, risk, time, and assumptions. The energy wall also includes waste heat, one of the least glamorous but most absolute realities in spacecraft design. Any powerful engine, reactor, laser receiver, or life support system creates heat, and in space, there is no air to carry that heat away. A spacecraft must radiate waste heat into darkness, using surfaces large and durable enough to glow invisibly or visibly with discarded energy. The more power the ship uses, the more serious thermal control becomes. An engine that can produce Starship-level power but cannot shed waste heat is not an engine. It is a delayed catastrophe. At high velocity, energy returns in another form: collision danger. A tiny grain of dust at ordinary speeds is an irritation. At a significant fraction of light speed, it becomes a projectile carrying devastating kinetic energy. The interstellar medium is thin, but not empty. Gas atoms, dust particles, and microscopic debris turn the forward direction of travel into a problem of shielding, detection, and sacrificial protection. Flying fast makes space itself feel denser, not because the medium changes, but because the ship's speed turns small encounters into violent events. So the energy problem is never only how to go. It is how to go, survive the going, stop after going, and keep the human world inside the vessel alive the entire time. This is why interstellar travel in one lifetime is not achieved by one invention alone. It requires propulsion, power generation, heat rejection, radiation management, structural materials, autonomous repair, navigation, shielding, and long-duration biology to mature together. A civilization that can accelerate a crude starship to 10% light speed is not simply a civilization with a better rocket. It is a civilization that has learned to handle energy at a depth we have only begun to approach. And yet, the wall is not the same as a locked door. Physics gives no obvious law saying humans can never reach another star. It says the payment is immense. With present technology, we buy the moon, Mars with difficulty, and robotic voyages across the solar system. With advanced nuclear systems, we may buy faster, stronger movement through the sun's realm. With fusion or beamed propulsion, perhaps one day we buy the nearest stars. But each purchase is heavier than the last, and the currency is energy, shaped by intelligence. In the quiet of the night sky, the stars do not move closer because we long for them. They wait behind equations, not cruelly, but honestly. The true wall of interstellar travel is not distance alone. It is the energy required to make distance small within a human life. And until humanity learns to gather, direct, cool, shield, and survive that energy, the nearest stars will remain exactly what they are tonight: visible, beautiful, mathematically reachable, and still almost impossibly far. A spacecraft built for a short mission can be imagined as a vehicle, a machine with a destination, a fuel supply, a navigation system, and a small, pressurized room where human beings endure the journey. But the farther that journey extends, the more this simple picture begins to dissolve, until a true deep space craft is no longer only an engine carrying people through emptiness, but a small, deliberate world, a sealed fragment of Earth wrapped in metal, mathematics, software, and trust. This is one of the deepest changes in thinking that happens when we move from ordinary spaceflight to the question of how far humans could travel in one lifetime. The limiting structure is not just propulsion, because even a perfect engine would be meaningless if the people inside slowly ran out of air, water, health, sanity, spare parts, or the quiet daily rhythms that make life feel livable. A rocket can give a spacecraft velocity, but only an artificial world can give human beings duration, and duration is the hidden dimension of distance. A few days to the moon can be survived with stored supplies, strict procedures, and a fragile but workable chain back to Earth. A many-month journey to Mars demands recycling, redundancy, radiation shelters, psychological endurance, and a crew able to act without immediate help. A decades-long voyage toward another star would require something far beyond a capsule. It would need a habitat that behaves less like a machine and more like an ecosystem, capable of renewing itself, repairing itself, monitoring itself, and preserving human life not for a dramatic launch, but through thousands upon thousands of ordinary mornings in a place where no natural morning exists. Air is the first invisible miracle. On Earth, we rarely notice the atmosphere because it is everywhere, pressing gently against our skin, carrying sound, scattering blue light, feeding every breath with oxygen, and diluting carbon dioxide into a planetary ocean of gas. Inside a spacecraft, air becomes an engineered substance, measured, filtered, circulated, dried, humidified, cooled, warmed, scrubbed of contaminants, and watched like a living patient. Carbon dioxide must be removed before it dulls the mind and harms the body. Oxygen must be replenished. Trace gases from plastics, electronics, human metabolism, cleaning agents, and equipment must not accumulate. Airflow must be designed so no sleeping crew member rests inside a pocket of stale, exhaled breath. The cabin atmosphere becomes a miniature climate system, and the farther the ship goes, the less it can depend on disposable filters or emergency tanks. Water is even more intimate, because water is both cargo and life itself, hidden in blood, cells, food, sweat, breath, urine, hygiene, cooling loops, and plant growth. A long-duration spacecraft must recover water from places that would feel emotionally strange on Earth but become ordinary in space. Humidity from exhaled breath, wastewater from washing, urine processed through chemical and physical systems until it returns as drinkable water. Not because the crew is desperate in some dramatic sense, but because closure is survival. Every % of recycling matters. A system that is 90% closed may sound impressive, yet over years the remaining 10% becomes a slow leak in the future. A starship, if such a thing ever carries people, would have to treat water almost like a sacred circulating organ, never merely stored, always returning. Food deepens the problem, because stored food ages, loses vitamins, occupies mass, and becomes psychologically heavy through repetition. For short missions, shelves of packaged meals can serve. For Mars, stored food plus limited fresh growth may be enough in early missions. For a truly long voyage, agriculture begins to move from luxury to infrastructure. Plants would not be decorative greenery placed beside a window for comfort, though they would bring comfort. They would be biochemical partners, converting carbon dioxide, releasing oxygen, recycling nutrients, offering fresh food, stabilizing humidity, and giving the crew a living rhythm that machines alone cannot provide. A leaf unfolding under artificial light inside a ship between planets is not a small thing. It is photosynthesis carried away from the sunlit world that shaped it. Yet, space agriculture is not simple romance. Plants require controlled spectra of light, root zone moisture, nutrient delivery, pollination strategies, disease monitoring, microbial balance, and energy. Every tomato grown in space is also an electrical calculation, a thermal calculation, a water calculation, a microbial calculation, and a psychological calculation. Waste, too, must change identity. On Earth, waste disappears into large systems: soil, sewage, oceans, microbes, weather, cities, rivers, landfills, treatment plants. In a spacecraft, there is no away. Away is still inside the mission. Human waste contains water, carbon, nitrogen, phosphorus, salts, and biological risk. Food scraps are not just trash, they are possible nutrients. Exhaled carbon dioxide is not only a contaminant, it can become plant matter or processed oxygen. The dream of a closed ecological life support system is essentially the dream of turning a spacecraft into a controlled metabolism. Not perfectly natural and not perfectly mechanical, but something in between, where chemistry, biology, and engineering exchange roles. Historically, this idea has roots in both space programs and Earth-based biosphere experiments, where researchers learned that closed systems are difficult not because life is weak, but because life is complex. Oxygen, carbon dioxide, soil chemistry, microbes, insects, water, crops, and human behavior interact in ways that can drift unexpectedly. A sealed world must be stable, but not dead, alive, but not chaotic. The same principle applies to machinery. A deep space ship cannot be designed as if repairs will arrive from Earth. The farther it travels, the more it must become its own workshop, warehouse, diagnostic laboratory, and manufacturing site. Pumps fail. Valves stick. Bearings wear. Electronics degrade. Seals age. Software develops unexpected behavior. Micrometeoroids and high-energy particles damage materials. A long voyage requires modularity, spare parts, additive manufacturing, robotic inspection, self-diagnosing systems, and crew training broad enough that a person may need to become engineer, doctor, farmer, electrician, mechanic, and systems thinker all at once. Redundancy is necessary, but redundancy has mass. Mass requires propulsion. Propulsion requires energy. Energy creates heat. Heat requires radiators. Radiators add structure. Structure adds more mass. A starship is therefore not a collection of separate problems. It is a web, and tugging on one strand moves the whole design. Artificial intelligence may eventually become the nervous system of such a vessel, not as a fantasy captain with a human voice, but as a tireless pattern recognition partner, watching pressures, temperatures, microbial trends, crop health, crew sleep, radiation events, vibration signatures, power flows, and tiny deviations that human attention would miss. But intelligence on board must be reliable, understandable, and repairable. In deep space, a black box system that cannot explain its reasoning may become a new kind of hazard. Autonomy is essential because communication delay grows with distance. Near the Moon, Earth can advise quickly. At Mars, messages may take many minutes one way. At Proxima Centauri, a message takes more than 4 years to arrive, and a reply takes more than 4 years to return. A crew traveling that far is not being remotely operated. It is politically, medically, emotionally, and technically independent. The ship must carry not only tools, but authority. Not only data, but judgment. Not only instructions, but culture. This is where the small world idea becomes most human. A vessel crossing deep space must preserve mental life, not merely biological function. People need privacy, shared ritual, beauty, variation, meaningful labor, education, conflict resolution, play, memory, and some form of horizon, even if that horizon is simulated by screens, lighting cycles, gardens, rotating observation schedules, or stories told beneath artificial night. The ship's architecture would shape the crew's mind. Narrow corridors, constant noise, poor lighting, lack of personal space, monotony, and unresolved tension could become as dangerous over years as a failing pump. Designers of long-duration spacecraft may need to think like engineers, doctors, architects, ecologists, and monks, because a world small enough to cross space must also be gentle enough to live inside. Gravity remains one of the most serious unresolved features of that world. If the ship simply coasts in microgravity for years, the body pays in bone, muscle, fluid regulation, and perhaps vision and immune function. Exercise can help, but it may not be enough for decades. Rotating habitats offer a possible path, creating artificial gravity through centripetal acceleration, where the floor presses upward because the structure turns. But that solution demands radius, mass, balance, structural strength, bearings or rotating joints, and careful spin rates so the inner ear does not rebel. A small rotating room spins too fast and feels strange. A comfortable rotating world must be large, and large structures are expensive to accelerate. Still, for lifetime-scale travel, some form of artificial or intermittent gravity may become not an elegant option, but a biological necessity. Radiation shielding also becomes part of world building. A spacecraft's living quarters may need to be buried inside layers of water, fuel, food, polymer, or other hydrogen-rich material. With a storm shelter for solar particle events and long-term strategies for galactic cosmic rays. On a planetary surface, regolith can be piled above habitats. In free space, every shield must be carried, arranged, and integrated into the ship's mass budget. The protective shell is therefore the artificial atmosphere's partner, replacing the sky and magnetic field Earth once gave freely. When all these systems are placed together, the answer to how far humans can travel becomes more exact and more humbling. Humans can travel only as far as their artificial world remains alive. The engine may define the ship's speed, but the habitat defines the ship's endurance. A spacecraft heading to Mars can be a robust expedition vehicle. A spacecraft heading to the outer planets must become a long-lived mobile base. A spacecraft heading toward another star within one lifetime must be a closed, repairable, shielded, psychologically sustainable, semi-autonomous biosphere moving at extraordinary speed. That is why interstellar travel is not simply the next chapter after rockets. It is the convergence of propulsion, ecology, medicine, computation, architecture, sociology, and ethics into one vessel. To go far, humans must stop thinking of the ship as an object and begin thinking of it as a place. A place where water remembers every breath. A place where plants turn electric light into food. A place where machines listen for their own illness. A place where children of Earth, even if no children are born on board, carry Earth's habits into a silence older than life. And perhaps the most haunting truth is that the farther we go, the less space travel resembles escape from Earth. It becomes the art of carrying Earth carefully, in miniature, through a universe that will not carry us otherwise. If we give a human spacecraft 1%, 10%, or 50% of the speed of light. The map of a lifetime changes so dramatically that the solar system begins to shrink behind us like a familiar shoreline. Yet even then, the universe does not become small. It only reveals a more exact scale of difficulty, because each rise in speed opens a new horizon while demanding a deeper payment in energy, shielding, navigation, deceleration, and human endurance. 1% of light speed sounds modest when spoken beside the full speed of light, almost like the first step on a long staircase. But in ordinary engineering language, it is already astonishing. About 3,000 kilometers per second, or roughly 1,860 miles per second, far beyond any crewed vehicle humans have ever built, far beyond the speeds that carried Apollo to the moon, and far beyond the cruise speeds of the robotic explorers now drifting through the outer dark. At 0.01 C, a spacecraft would cross the distance from Earth to the moon in a little over 2 minutes, not days. It would reach Mars, when conditions were favorable, in mere hours rather than months. It would pass the orbit of Jupiter in a few days, and the realm of Neptune in less than 3 weeks, turning the vast architecture of the solar system into something that finally feels traversable within ordinary human planning. Yet the moment we look beyond the Sun, the old immensity returns. Proxima Centauri, the nearest known star to the Sun, lies about 4.25 light-years away, and at 1% of light speed, a simple cruise calculation gives a travel time of about 425 years before allowing for acceleration, braking, course correction, system failures, or the practical fact that a human mission must do more than flash through a destination. This is the quiet lesson of 0.01 C. It would revolutionize human travel inside the solar system, and perhaps open the nearby interstellar medium to direct human exploration. But it would not make the nearest star reachable in one ordinary life. It would be a speed for descendants, archives, and long-lived machines, unless biology itself were changed, suspended, or carried through generations. And each of those possibilities belongs to a different category of civilization. 10% of light speed, 0.1 C, is the first threshold where the stars begin to enter a human lifetime in a serious mathematical sense. At 0.1 C, a craft covers 1 light-year in 10 years, so Proxima Centauri could be reached in roughly 42 or 43 years of cruise time in an idealized straight-line journey. And the Alpha Centauri system, sitting at nearly the same distance, becomes not close, but no longer mythical. A young astronaut leaving in their 20s might arrive in old age, having spent most of adult life inside an artificial world, moving through interstellar darkness. Barnard's star, about 6 light-years away, would take around 60 years at this speed, and Sirius, more than 8 light-years away, would require more than 80 years, already straining or exceeding a normal human lifetime, if we count the time needed to slow down and do anything meaningful after arrival. This means 0.1 C does not open the galaxy. It opens only the first few doors in the local stellar neighborhood, a small cluster of nearby suns that becomes visible as destinations only when the spacecraft is already moving thousands of times faster than our current crewed vehicles. The energy scale at 0.1 C is severe. In a classical approximation, the kinetic energy of a moving ship rises with the square of velocity. And while relativity is still moderate at 10% light speed, the amount of energy required to accelerate a large, shielded, life-supporting habitat becomes civilization scale compared with present mission budgets. A gram-scale probe might be imagined differently from a 1,000-ton habitat because mass is the silent multiplier of every velocity dream. A small robotic sail can be pushed by lasers in some advanced concepts. A human vessel must carry water, air, radiation shielding, medical equipment, power systems, thermal control, living volume, redundancy, and perhaps a rotating section for artificial gravity. At 0.1 C, dust grains become dangerous because kinetic energy turns small impacts into violent events. Navigation must be exquisite. The forward shield is no longer a minor protective layer. It becomes one of the defining structures of the ship. And then comes the often forgotten problem of stopping. If a crewed spacecraft reaches Proxima at 10% light speed and cannot decelerate, the star system would sweep past like a continent glimpsed from a bullet train after 40 years of crossing an ocean. Arrival requires braking, and braking requires energy, propellant, sails, interaction with stellar wind, magnetic fields, or infrastructure not yet present at the destination. So 0.1 C gives us the first honest Starship lifetime, but it gives it with a warning written into every equation. Reaching the speed is only half of reaching the star. 50% of light speed, 0.5 C, changes the feeling of the map again. At this velocity, Proxima Centauri lies only about 8.5 years away by Earth's calendar in a simple cruise estimate, and stars 20 light-years away can be imagined as destinations within 40 years of travel. So the local bubble around the Sun begins to look less like an unreachable ceiling and more like a dark ocean dotted with islands. A traveler moving at half light speed could, in principle, cross distances that would make 0.1 C feel patient and 0.01 C feel ancient. But 0.5 C also crosses into a more visibly relativistic world. The Lorentz factor at half the speed of light is about 1.15, meaning time dilation is real, but not yet extreme. A journey measured as 8.5 years from Earth would feel somewhat shorter to those on board, but not magically brief. More importantly, the energy of the spacecraft becomes enormous. The kinetic energy is not just 5 times greater than at 0.1 C. In rough classical scaling, because velocity has increased by a factor of 5, the energy rises by about 25 times for the same mass, with relativistic corrections adding more. A ship at 0.5 C is not merely fast, it is an object carrying such concentrated motion that every design choice becomes moral as well as technical. A collision with even a modest object could be catastrophic. The interstellar medium, thin as it is, becomes a stream of high-speed particles arriving from the front. The ship may need layered sacrificial shields, active detection, perhaps magnetic or plasma-based deflection systems, and a long forward architecture built less like a nose cone and more like a moving storm shelter. Light itself begins to change character. Stars ahead are shifted slightly toward higher energies, stars behind toward lower, and the sky would not look exactly like the slow, calm celestial sphere seen from Earth. The universe would appear directionally transformed by motion, not because the stars changed, but because the traveler's frame of reference has. If we imagine accelerating gently enough for humans, the timeline gains another layer. A ship does not instantly appear at 0.1 c or 0.5 c. If it accelerated at something like 1 Earth gravity, the crew could feel a comfortable downward force while gaining speed, but sustaining that acceleration requires tremendous power and propellant or some external energy system. Reaching 0.1 c at 1 g would take on the order of weeks, while 0.5 c would take many months in a more careful, relativistic treatment. And then the ship would need a comparable period to slow down, unless the mission accepted a high-speed flyby. Lower accelerations may be easier on engineering, but stretch the mission. Higher accelerations may shorten the burn, but strain the body and structure. The neat arithmetic of distance divided by speed is therefore only the skeleton of the answer. A real trajectory has muscles, joints, fuel lines, heat radiators, and human limits. At 1% light speed, one lifetime still belongs mostly to the solar system and the space just beyond it. At 10% light speed, the nearest stars become possible one-life destinations, but only as extreme, decades-long commitments by a civilization able to build a self-repairing, shielded, autonomous world ship. At 50% light speed, a portion of the local stellar neighborhood opens within human time, though the cost rises into a realm where propulsion, energy storage, heat rejection, collision protection, and braking may be more difficult than the act of pointing at the star itself. The progression is not just faster, faster, faster. It is a change in the meaning of travel. At 0.01 c, humans would become masters of the solar system. At 0.1 c, they would become true interstellar travelers, but only to the nearest lights. At 0.5 c, they would begin to live inside relativistic geography, where distance, energy, time, and danger all become sharper. And still, the Milky Way would remain vast beyond ordinary intuition, because a galaxy more than 100,000 light-years wide cannot be conquered by a single lifetime, unless one invokes velocities extremely close to light speed and accepts the deep relativistic separation between traveler and home. So the answer hidden inside these three numbers is both hopeful and calming. 1% of light speed would make the solar system feel almost open. 10% would bring the nearest stars into the long reach of a human life. 50% would make the local stellar neighborhood navigable in principle, though at a price no current civilization can yet pay. The stars are not moved by our longing, but they are not sealed behind magic either. They wait behind ratios, energies, shields, and clocks. And as each speed rises, the universe gives a little more distance while asking humanity to become a little more careful, more powerful, and more worthy of carrying life across the dark. Time feels absolute only because human life is slow. because our bodies move through ordinary days at ordinary speeds, watching clocks agree closely enough that we can believe there is one universal river carrying everyone forward together. But near the speed of light, that familiar river begins to separate into channels, and the question of how far a human can travel in one lifetime becomes stranger, deeper, and more beautiful than distance alone. In the physics of Isaac Newton, space and time were treated as a kind of silent stage, firm and independent, where objects moved, forces acted, planets curved around the sun, and a clock in London could be imagined to measure the same time as a clock on Jupiter, if both were perfect. That picture worked with extraordinary accuracy for falling stones, cannonballs, tides, bridges, machines, moons, and planets. And it still guides much of spaceflight today, because rockets leaving Earth and spacecraft transferring between planets usually move far below light speed. But in the early 20th century, Einstein changed the background itself by asking, what must be true if the speed of light is the same for all observers moving uniformly, a fact suggested by electromagnetic theory and later supported by experiment? And the answer was not that light adjusts itself to fit ordinary time, but that ordinary time and ordinary distance adjust themselves to preserve light's speed. This is the doorway into special relativity, where time is no longer a single cosmic heartbeat shared by all travelers, but a measurement that depends on one's path through space-time. The mathematical heart of this effect is often written through the Lorentz factor, gamma, equal to 1 divided by the square root of 1 minus velocity squared over light speed squared. And although that expression may seem cold on the page, it carries a quiet revolution. As velocity becomes a larger fraction of light speed, gamma increases, and the moving traveler's clock, as seen from Earth, runs more slowly. At everyday speeds, gamma is almost exactly 1, so the difference hides beneath perception. Even spacecraft speeds around Earth produce only tiny relativistic corrections, important for precise systems like satellite navigation, but not enough for astronauts to feel as though they have slipped out of history. At 50% of light speed, gamma is about 1.15, meaning the effect is real but not yet overwhelming. At 90% of light speed, gamma rises to about 2.29, so a traveler could experience roughly 1 year, while Earth measures more than 2. At 99% of light speed, gamma is about 7.09, and now the separation between onboard time and Earth time becomes large enough to reshape the meaning of a voyage. Nothing magical has happened, and nothing has exceeded light speed. The traveler is simply following a different path through space-time, and the length of that path, measured as proper time by the traveler's own clock, is shorter than the time recorded by observers who remain near Earth. This is why the phrase "one lifetime" must be handled carefully. A lifetime, according to Earth's clocks, is one kind of boundary. A lifetime, according to the traveler's own body, is another. If a ship travels to a star 4 light years away at a modest fraction of light speed, the difference may not be dramatic. But if a ship travels at extreme relativistic speed, the person aboard may age far less than the people waiting at home. The universe does not let the ship outrun light, but it allows the traveler to experience the journey differently, because time itself is part of the geometry being traveled through. From Earth's perspective, the star remains light years away, and the ship takes years to arrive. From the ship's perspective, the distance in the direction of travel is contracted, a companion effect called length contraction. So the gulf ahead is physically measured as shorter in the traveler's frame. The crew does not feel their own watches slowing down. Their hearts beat normally. Their plants grow according to local chemistry. Their conversations unfold in ordinary seconds. Their meals cool. Their dreams pass. Their bodies age, and their instruments behave as if they are at rest inside their own vessel. It is Earth, seen through the mathematics of relative motion, that appears altered, and when signals are exchanged, both sides must account for motion, Doppler shifts, travel time of light, acceleration history, and reference frames. The emotional consequence is almost larger than the physics. A relativistic voyage is not just a journey through space. It is a journey away from shared time. If a traveler leaves Earth, accelerates to a speed very near light, crosses a great distance, slows down, and later returns, they may find that Earth has aged more than they have. This is sometimes called the twin paradox. Although it is not a true paradox once acceleration and space-time paths are properly understood. The traveling twin changes inertial frames and follows a different world line, and the difference in elapsed time is measurable, not philosophical. What makes it haunting is not confusion, but clarity. A human being could, in principle, use relativistic motion to reach distances that would otherwise exceed a biological lifetime. But the price is paid in the time of everyone left behind. The farther and faster the journey, the more the traveler becomes a person displaced not only in space, but in history. A voyage to a nearby star at 90% light speed might reduce onboard aging noticeably while still keeping Earth within a recognizable future. A voyage across hundreds or thousands of light years at far higher gamma could allow the traveler to experience decades while Earth measures centuries or millennia. But such a journey would no longer be an expedition returning to the same society. It would be a migration into the future, a crossing where the homeworld becomes an ancestor. This distinction matters because relativity can easily be misunderstood as a loophole when it is really an exchange. It does not remove the need for propulsion. It does not remove the need for energy. It does not remove the danger of dust, radiation, heat, navigation, or deceleration. In fact, the closer a ship moves to light speed, the harder these problems become. The kinetic energy of the vessel rises enormously, and even sparse interstellar gas becomes a stream of particles striking from ahead with dangerous energy. Background light is shifted in frequency. The forward sky compresses visually through relativistic aberration, with starlight crowded toward the direction of travel, while the universe behind changes in the opposite way. The ship would need shielding far beyond ordinary spacecraft, perhaps layered material, electromagnetic protection, sacrificial structures, or active systems not yet demonstrated at such scales. It would also need a way to accelerate gently enough for humans to survive and then slow down at the destination, because racing past a star at 99% light speed is not the same as arriving. One of the most elegant thought experiments is a ship accelerating at one Earth gravity for half the trip, then turning around and decelerating at one Earth gravity for the second half. Inside, the crew would feel a downward pull similar to Earth's gravity, solving part of the long-duration microgravity problem while producing enormous velocity over time. In such idealized calculations, relativistic effects can make distant stars reachable within surprisingly short proper times for the travelers. But the word idealized carries weight. Maintaining one gravity of acceleration for years would require power and propellant or external energy on a scale far beyond present engineering. Heat rejection would be immense. Structural reliability would need to be almost sacred. The navigation problem would sharpen with every fraction of light speed. So relativity opens a door in the laws of nature, but engineering has not yet built the hallway leading to it. This is the deep balance of the chapter. Time dilation means a human lifetime is not an absolute cage, yet it does not make interstellar travel easy. It says that if civilization one day learns to command extraordinary energy safely, a person might cross distances that seem impossible under earthbound intuition, aging less than the world they left, seeing the galaxy not by breaking physics, but by moving through space-time along a path where less proper time passes. The stars remain far for Earth. They may become less far for the traveler. And between those two truths lies one of the most profound costs of becoming a relativistic species. To go farther in one life, one must loosen the bond with the time of home. The traveler's lifetime becomes a narrow lantern carried forward, while the centuries of Earth burn behind it. In that sense, time dilation is not merely a technical effect. It is the universe whispering that distance and time are woven together, and that every attempt to cross the great dark must decide which clock it is willing to obey. By the time we reach the deepest edge of this question, the words "one lifetime" no longer feel as simple as they did at the beginning, because space has quietly forced us to ask, who is holding the clock? The people on Earth, aging beneath weather and seasons, or the traveler inside the ship, moving so fast that time itself begins to loosen from the rhythm of home? At ordinary speeds, this distinction hardly matters. A crew going to the Moon, Mars, or even the outer solar system may experience small relativistic differences too tiny to shape the story in any human way. So a year on the spacecraft and a year on Earth remain close enough for mission planning, birthdays, medical records, and memory to feel aligned. But once we approach a significant fraction of light speed, the phrase "within one human life" splits into two meanings, and each meaning gives a different map of the universe. If we measure by Earth's clocks, a human lifetime is a strict external boundary, the lifetime of a civilization watching a spacecraft cross the dark from a familiar reference frame. If we measure by the traveler's own clock, a lifetime becomes proper time, the time carried along the traveler's path through space-time, the time measured by their heartbeat, their meals, their sleep, their aging cells, and their own onboard instruments. This difference is not philosophical decoration. It is one of the central facts of special relativity, and it turns the final answer from a single number into a layered horizon. According to Earth, Nothing with mass can be accelerated to the speed of light or beyond it. So, in an 80-year Earth lifetime, no ship leaving Earth can reach farther than 80 light-years in any direct sense. And in reality, it must reach less than that, because it needs time to accelerate, time to decelerate, energy to maneuver, and some margin for survival. At 10% of light speed, the ship covers about 8 light-years in 80 years of Earth time, enough to include Proxima Centauri and a few nearby stars, but not enough to make the galaxy feel open. At 50% of light speed, it might cover about 40 light-years in that same Earth lifetime. And now, dozens or perhaps hundreds of stellar systems enter the wider neighborhood, depending on direction and mission design. Yet even this is still a tiny bubble inside a Milky Way more than 100,000 light-years across. At 90% of light speed, an 80-year Earth window reaches toward 72 light-years in simple distance, before accounting for acceleration and braking. And although that sounds vast, it is still not an empire of stars. It is only a local candle circle in a galactic night. Earth time travel is therefore severe but clear. One lifetime on Earth can never hold the whole galaxy. An even advanced relativistic spacecraft would remain limited to a small region unless the travelers accept that Earth will wait far longer than their bodies do. From the traveler's point of view, however, the universe becomes stranger. At high speed, time dilation reduces the amount of time that passes aboard the ship compared with Earth, and length contraction reduces the distance to the destination in the direction of travel as measured in the ship's frame. A star that is many light-years away according to Earth can become a shorter journey in the traveler's own experienced time if the ship moves close enough to light speed, not because the ship cheats causality, and not because it outruns light, but because space-time gives different observers different measurements of distance and duration, while preserving the same deep physical laws. A traveler moving at 90% of light speed has a Lorentz factor of about 2.29, so the onboard time for a long cruise is less than half the Earth-measured time, ignoring acceleration phases. At 99% of light speed, the Lorentz factor is about 7.09, so Earth can measure more than 7 years for every 1 year experienced on board during the high-speed portion. At 99.9% of light speed, the factor rises to about 22.4, and suddenly, a voyage that Earth sees as centuries long might fit into decades for the traveler, though only by demanding energies and protections so extreme that they remain far beyond demonstrated engineering. This is the strange generosity and severity of relativity. It does not forbid a person from experiencing a journey to very distant places within a biological lifetime, but it charges the cost to energy, shielding, acceleration, braking, and separation from the time of home. If a person travels far enough and fast enough, they may arrive still alive, still themselves, still carrying memories from Earth, while the Earth they remember has become history. This is why the final limit is not just physics, but belonging. A Mars crew may return to the same generation that watched them launch. A crew traveling to Proxima at 10% of light speed might still be linked to the same historical age, though faintly, with parents gone, children old, institutions changed, and the first reply from Earth after arrival taking more than 4 years to arrive. But a crew traveling at extreme relativistic speed to a star hundreds of light years away may leave behind not only family, but era, language, politics, climate, culture, and perhaps the entire social meaning of their departure. They would not simply be explorers, they would be emigrants from a moment in time. The farther they go by their own clock, the more Earth becomes not a place waiting in real time, but an ancestral signal moving behind them at light speed. A radio message sent home from such a voyage may arrive to people who know the travelers only as names in an archive. A message from Earth may reach the ship after the senders have been dead for generations. In ordinary exploration, distance separates bodies. In relativistic exploration, distance separates histories. The practical mission categories become clearer when seen this way. A one-way journey, measured by the traveler's lifetime, can reach farther than a round trip measured by Earth's lifetime. A flyby can reach farther than an arrival, because slowing down consumes enormous energy or requires interaction with the destination system. A mission that only sends data can go farther than a mission that must keep humans alive and active. A mission that allows the traveler to lose synchronization with Earth can reach farther than one that insists on returning to the same civilization that launched it. These distinctions matter because popular imagination often compresses them into one phrase: going to another star, as if a probe flyby, a crewed flyby, a crewed landing, a permanent settlement, and a round-trip expedition were variations of the same difficulty. They are not. They are different physical stories. To fly past Proxima at high speed is one kind of achievement. To slow down and enter orbit around a world, there is another. To live there is another. To return to Earth before everyone you knew is gone is another still. The universe becomes more honest when each version is named. The deepest answer, then, is that the ultimate boundary of one lifetime travel depends on which clock defines the mission and what counts as arrival. If the clock is Earth's and the mission requires meaningful arrival, then even very advanced ships are limited to nearby stars within a human lifetime, perhaps tens of light years under extremely ambitious assumptions. If the clock is the traveler's and the ship can move extremely close to light speed, then physics allows much greater distances in principle, perhaps hundreds or thousands of light years within the traveler's experienced decades. But Earth would age far more, and the technological requirements move into a realm we have not yet learned to command. If the mission must return to Earth and remain part of the same human generation, the range collapses sharply. If the mission is allowed to be one-way, autonomous, and historically detached, the range expands. And if the mission is only a mathematical possibility under ideal acceleration, unlimited energy, perfect shielding, and flawless repair, it belongs not to present astronautics, but to the far horizon of theoretical civilization. There is no shame in that. Science often begins by separating what nature permits from what engineering can yet build. Nature appears to permit relativistic travel below light speed. Engineering has not yet given us a human starship. Biology has not yet shown that it can thrive for decades inside a closed vessel moving through interstellar radiation. Society has not yet decided what kind of journey would justify leaving its own time behind. So the final limit is not a wall with one inscription. It is a set of nested boundaries. the speed limit of light, the energy needed to approach it, the body's ability to survive the trip, the ship's ability to remain a world, the destination's requirement for braking, and the emotional cost of letting Earth's clock drift away from your own. A human lifetime seen from Earth is a bright but narrow measuring rod laid against the dark. A human lifetime carried aboard a near light-speed ship is a private flame moving through a different geometry of time. Both are real. Both answer the question. And between them lies the quiet truth that to travel farther than our ancestors could imagine, we may one day have to choose not only where we are going, but which version of time we are willing to leave behind. The final answer is not a single distance, but a set of nested distances, each one belonging to a different version of humanity. And the deeper we look, the quieter the answer becomes. With the technology we have actually demonstrated, humans can realistically travel within the inner solar system, from Earth orbit to the Moon, and eventually, with enormous difficulty, to Mars. With major but still physically conservative advances in propulsion, radiation protection, closed life support, and autonomous medicine, humans might extend their lived frontier to asteroids, deep space habitats, and perhaps one day the moons of the outer planets. With revolutionary propulsion reaching a meaningful fraction of light speed, the nearest stars enter the edge of a human lifetime. And with relativistic flight close enough to light speed, a traveler's own lifetime could carry them much farther, though only by allowing Earth's time to flow away behind them like a river they can no longer return to unchanged. This layered answer is more honest than a dramatic number, because distance in space is never just geometry. It is velocity, energy, time, biology, shielding, braking, psychology, and the ability to keep a small artificial world alive long after the planet that built it has become only a bright point in the rearward dark. If we speak from the present, the answer is modest but not small. The Moon is proven, Mars is the next great human threshold, and the deeper solar system remains more suitable for robots than crews, until our machines become far more self-sufficient and our habitats far more Earth-like. If we speak from the near future, a human life might include voyages that make the Moon feel local, Mars difficult but familiar, and near-Earth asteroids or orbital construction yards part of a growing human economy beyond Earth. Yet even then, Proxima Centauri would remain outside reach, not because it is forbidden, but because it belongs to the scale of light years, while our present craft still belong to the scale of kilometers per second. If we speak from the era of true starships, the first meaningful threshold is around 10% of light speed, where Proxima Centauri becomes a journey of roughly 4 decades in an ideal cruise calculation, turning the nearest star from a mythic destination into a lifetime commitment. At 20% of light speed, nearby stars become more accessible in human terms, though energy and shielding become severe. At 50% of light speed, the local stellar neighborhood opens in principle, but the spacecraft becomes a kinetic object of terrifying power, a moving biosphere that must survive dust impacts, radiation, waste heat, navigation errors, and the equal necessity of slowing down after arrival. If we speak from the far edge of known physics, special relativity tells us that a human lifetime measured on board a near-light-speed vessel can reach farther than a human lifetime measured on Earth, because the traveler's proper time can be shorter than Earth's coordinate time. But this is not escape from physics. It is a trade with it. The traveler gains distance by losing synchronization with home. The stars become nearer to the body, while Earth becomes older to history. This distinction matters because it prevents the answer from turning into fantasy. A person might, in principle, cross hundreds of light years within experienced decades if a civilization could provide extreme velocity, extreme protection, extreme reliability, and controlled acceleration and deceleration. But Earth would watch centuries pass, and the traveler would arrive not merely in another place, but in another era. So the most complete answer is this. Humans today can go to the moon and may soon attempt Mars. Humans with advanced solar system technology could live and travel across the sun's realm. Humans with interstellar propulsion at 10 to 50% of light speed could reach the nearest stars in one life. And humans with near light speed relativistic craft could travel much farther by their own clocks, but not without paying in energy, danger, and separation from the time of Earth. And perhaps this is why the universe still feels so silent. The silence of the sky has many possible explanations, and no serious mind should pretend that one answer has been proven. Life may be rare. Complex life may be rarer. Intelligence may be fragile. Civilizations may not last long enough to cross between stars. Some may choose not to expand. Some may communicate in ways we do not recognize. Some may be separated from us by time more than by space, rising and fading long before our instruments began listening. But one possibility, sober and powerful, is that interstellar travel is simply hard in the same way for everyone. Not impossible, not magical, not guaranteed, but hard enough that even a brilliant species might remain close to its home star for a very long time. The galaxy may be filled not with empires moving easily from sun to sun, but with islands of intelligence learning slowly beneath their own skies, each one looking outward, each one discovering the same equations, each one realizing that the distance between stars is not an empty road, but a filter made of energy, time, risk, and endurance. This does not solve the Fermi paradox, but it softens it into something more physically grounded. If every civilization must face the rocket equation, radiation, life support, propulsion limits, dust impacts, communication delay, social stability, and the immense cost of crossing light years, then the silence may not be mysterious in a simple way. It may be the natural sound of a universe where intelligence can awaken long before it can travel far. Radio signals are easier than starships, but even signals weaken, spread, miss targets, pass through eras when no one is listening, or arrive as patterns too faint or too unfamiliar to identify. A civilization may announce itself for only a brief technological window, or may become quiet by choice, or may use tightly directed communication instead of broadcasting wastefully into the dark. And even if someone out there has crossed between stars, the galaxy is so large and so old that their path may never have crossed ours. Their signals may not be aimed at us, and their evidence may be hidden in scales of engineering we have not yet learned to read. In that way, the silence above us is not empty. It is unfinished evidence. It is a question spread across 100 billion stars. It is the space between what physics allows and what civilizations actually survive long enough to do. For humans, the practical lesson is gentle but demanding. Before we become interstellar, we must become sustainable. Before we carry life to other stars, we must learn to keep life stable in closed worlds. Before we dream of crossing the galaxy, we must learn to cross the distance between Earth and Mars without treating the human body as an afterthought. The first starship, if it ever carries people, will not be born from speed alone. It will be born from a civilization that understands water, air, soil, radiation, trust, autonomy, medicine, heat, power, and time as parts of one design. It will be a vessel of equations and gardens, reactors and sleeping quarters, shields and songs, navigation charts and private grief. A place where the old Earth continues in miniature while the real Earth falls farther behind. That is why the answer to how far humans can travel in one lifetime is finally also an answer to what humans are. We are not light. We are not machines. We are slow creatures from a wet planet, carrying fragile bodies and enormous ideas into a universe that does not bend to our urgency. Yet, we are also the species that learned the stars are suns, that gravity has equations, that time can dilate, that atoms can release stellar energy, that a spacecraft can become a temporary world, and that a single lifetime can hold enough curiosity to reach beyond every horizon it was born under. So tonight, if you look upward and wonder how far one human life could go, the most truthful answer is both small and immense. Not across the galaxy yet, not easily to another star today, but far enough to begin changing the meaning of home, far enough to place footprints on another world, perhaps shelters under alien dust, perhaps ships between planets. And one day, if our descendants master energy with wisdom, far enough for someone to watch our sun become just one more star behind them. The universe remains silent, not because it has nothing to say, but because its sentences are written in light years, and every civilization must learn, slowly, how to read them. And perhaps that is the quiet truth of space travel. One lifetime may not carry us across the galaxy, but it can carry us far enough to change what home means. If this journey brought you peace or wonder tonight, please like, subscribe to Sleepy Space, and tell us in the comments where you're listening from.